All right, so we'll talk. We'll continue on discussing Bootstrap. So I uploaded just this script onto CCLE, so you can download it. And we left off on Wednesday covering nonparametric bootstrap. So again, Bootstrap is used when you have done random sampling from the population, and therefore your sample can be expected to be representative of the population. And when you do Bootstrap, you are simulating basically the random sampling process, and you're going to sample with replacement from your sample. Okay, and this effectively takes your current random sample and makes a million duplicates of it so that it acts as the population. Okay. And that's in contrast to, I'm sorry, did I say parametric? Or I don't remember what I said. Okay, so that was non-parametric bootstrap, where you are sampling with replacement from your sample. And parametric bootstrap is you are sampling from a known distribution. Okay, so parametric bootstrap puts assumptions on the population as far as the distribution of the population goes, and non-parametric bootstrap does not. It just basically duplicates your population. So I believe we left off, and we were taking a look at this data file that looked at immigrants from Latin American countries, and we are contrasting immigrants from Mexico versus non-Mexican immigrants. Okay, and we want to, and the researchers are looking at the level of educational achievement in these studies. So we're going to take a look there, and from that, so anyway, I load up this data set. We can take a look at the data, and we see there is a difference between those from Mexico and those who aren't from Mexico in their mean educational achievement level. Okay, and the question, as always in statistics, is this difference significant? So one is, there are a few pieces, right? One is it statistically significant, meaning that is this something that could have resulted from random chance versus it didn't result from random chance? And then the other ones, which require more than just statistics and probability, but a little bit more knowledge of the subject matter, is this difference even important? Okay, so perhaps you have a statistically significant difference of 2 points, but if 2 points doesn't really make a huge difference, maybe we don't care. Okay, it's like you go to the grocery store, and are you going to pay $1.79 for a bottle of soda, or $1.89 for a bottle of soda? It's a 10-cent difference, and maybe it's a significant thing, but maybe it doesn't really matter. Okay. Versus, in other cases, maybe such a difference is quite big. So we looked at, in parametric bootstrap, we randomly sampled this to just kind of get an approximate p-value, okay? And the code I ran in class is kind of this manual method, right? We're setting up a vector to record the differences, and then I run this loop where I'm just going to randomly sample with no, this one's the parametric, sorry, not parametric. Okay, we're going to randomly sample with replacement from our pretend population, which is just the vector of educational achievement levels. Okay, so we just randomly sample from there. We split that into 2 groups. We take the mean of each of those groups, and we record the difference of those means in our difference vector. Okay, so I can just run this loop 10,000 times. I can take a look at kind of the histogram of our differences, and this would be this is after 10,000 of them. We can plot a density of those differences, and this is what our density plot looks like, our estimated density of our 10,000 differences. And what we have is an, whoops, okay. Well, that's too bad. Let me just, okay, so we'll do that. Let me just plot the density of our differences. Okay, so this is what we have after 10,000, and we can kind of get an approximate. What just happened here? Okay. And let me just calculate the observed difference here. Okay, and we can get an approximate p-value after calculating, those 10,000 differences. We can see how many of those differences are greater than 5.9. Okay, and in this case, we got about 5% of them. Okay, and so this is kind of our estimated p-value here. This seems a little strange. Let me just. Okay. Another thing we can do is we can use the boot library in R. R has a library called boot, and this is for doing bootstrap. And the way the boot function works, oops. If you look at the help topic for bootstrap resampling, okay, it asks the two biggest things is the data, the statistic that you want to calculate, and the number of replications. Okay, so the statistic, if you look at this, let's see if I can. It says it's a function which, when applied to the data, returns a vector containing the statistics or statistics of interest. All right, and it can do both parametric and non-parametric, but in general, I would recommend this for using the non-parametric case. All right, and so in this case, the statistic that we're interested in is the difference between the mean of group 1 and the mean of group 2. Okay, and so as far as calculating this applied to our data set, okay, our data set is the Latino education data set. So, again, we can look at head Latino, and we're basically just looking at the column achievement, and we want to split that, okay? And so what boot will do is that it takes this data set and it resamples from it with replacement, and then it applies, it's going to just apply this function to the data set, okay? So currently I can just take, I can program this function in, and then I can say, what is the mean difference of our current data file, okay? And it runs. Okay, so all this function is doing is it's a function of data. You often have to throw in indices, but it's not even, sometimes it's not necessary. So don't worry too much about that. We're just saying, here's our data. I'm sorry, yeah. We take our function and our indices, and basically what the boot function does is it takes the data and it just resamples the 150 indices with replacement. Okay, and so inside your function, you're gonna say my data is this, and then from that data, you're gonna calculate the statistic that we're interested in. So this is what we're doing. So this is our function, and then we run the let me just show you the command for running nonparametric bootstrap, is you just say boot, data is your data file, data from Latino, and then our statistic is going to be this function that we created, and we're going to do 5,000 replicates. The book talks about adding this little correction factor, and that's why we do one less than 5,000, but don't worry too much about it. The correction factor, once you get to 5,000, is hardly anything. Yes, question?
For the function, do you have to store the data to D, or you just feel like doing so?
I just felt like calling it D, okay? But you should, because the way the bootstrap function works, the way the boot function works is, so over here, I said randomly sample, and we're sampling from pretend population. So this thing, random sample, is an actual vector of values, okay? With the boot function, what it does is it creates a vector of indices. So if it looks at the data file or data frame Latino and it sees it has 150 rows, what it's going to do is it's going to just randomly sample with replacement 1 through 150, okay? And so it's going to return back, 5, 7, whatever, and we're basically going to subset our data frame using those indices. And this is effectively doing the same thing as this, okay? But this is just the way the boot function works, is that it provides a vector of random indices, and so we have to subset our data on that, and using that we calculate the statistic that we want. Okay, so this is the statistic it's going to return, and so we can do that, and then we just run it. Okay, so we do that. Nonparametric boot. If we look at the structure of what the boot function returns, we can take a look. Okay. And we see, it's got a whole bunch of stuff. T is the vector of all of the values returned with each iteration of running this, each replicate of the bootstrap. Okay, so T is kind of the equivalent of our difference vector over here. So over here we ran this, and then we kept track of every difference that we calculated. The non-par boot $T would be the equivalent of that thing, okay? And then everything else is kind of just some other stuff that goes on in case we wanted to repeat these things, okay? Okay, so this is non-parametric boot, and then so the results are all non-par boot $T, so we can plot the density of that, and this is what it looks like. So it looks quite similar to our density from, let me see, when I did density of the difference, and this is what happens when you run it with the boot function. Okay, so they're pretty much the same thing, right? Okay, and we can ask, what's the mean of all of those things, and we can also get an approximate p-value. Okay, so right around 5%, just a tiny bit under. So we would say something around, moderate evidence here. Okay. In homework 6, there's going to be some reading that I'm going to have you guys do, and I'm going to have you do a lot of reading on p-values. Maybe not a lot, but some reading. Okay. I don't know if you guys are aware, but there's been a lot of complaints levied against p-values in general. All right, and so this, and actually the American Statistical Association earlier this year released their kind of official stance on p-values, and it generated a lot of controversy. Okay, and I think p-values are great, but I do agree that p-values have been misused, and a lot of people don't fully understand how they're supposed to be used. So anyway, that'll be part of your reading here. I don't know how I'm going to write good questions on p-values, but like have you write an essay. I don't think that's no one laughed, right? Yeah, we chose statistics to avoid essays, right? So Maybe not to avoid essays, but that's what we're hoping. Okay. So anyway, so that's how the boot function or in R works. Okay, so you have to provide it with a function here. Okay, there's another way that we can talk about the difference that we've observed. Okay, so the difference that we've observed in our data, okay, if I look at the observed difference, which was calculated by taking the mean of achievement scores, where I've subsetted, see, this is old school before dplyr, right? So I've basically taken the difference of these, and I got this value here. We can talk about what would this p-value here, this approximate p-value here, be if instead of assuming a difference of 0, okay, what if we assumed there was a different difference, okay? And this is talking about effect size. So I think in 101B, where you do design of experiments and stuff, you learned about effect size. Okay? No? Maybe? You haven't taken it. Okay. So effect size is this concept that, okay, so maybe we're going to say this group and this group are not the same population, right? So this group has one mean and this group has another mean, okay? But if the difference between the mean of this group and the difference between the mean of this group is negligible, okay, then maybe it doesn't really matter. If the effect size is small, maybe it doesn't matter, okay? And maybe we only care if the effect size is greater than a certain value, okay? And so we can kind of test, see if our the data that we have displays a difference between sample means of about 5.9. Okay, and we can ask, is 5.9 significant for this effect size? Is it significant for this effect size? And we can kind of test a range of effect sizes and see if it's significant or not. Okay, so you know, right now, if we're assuming an effect size of 0, meaning that people coming from Mexico and people who did not come from Mexico have a difference of 0 in their educational achievement levels, the p-value is around 0.047, which we would say is something like moderate evidence. Okay, not super strong, but it's not something that we can completely ignore. So basically, all we have to do is we're just going to, in effect, we're just going to shift this distribution along the axis here. Okay, so right now it's kind of centered with the assumption of 0. You know, what would happen if we shifted it along? Okay, so right now we are centering it at 0, and I'm effectively drawing a bar at 5.9 and negative 5.9, and I'm shading in the area to the left and to the right to kind of get this idea of, you know, what is the p-value here? Okay. When we're talking about effect sizes, we're going to have only one-sided tests, okay? Because the effect sizes, we are hypothesizing a difference. You know, we might say we're assuming the difference between group 1 and group 2 to be 0. And now we're interested in if it's only 5.9 or greater. And as we shift these effect sizes from the low end to the high end, this idea of observing our data or something more extreme is going to switch from looking at the area to the right or looking at the area to the left, okay, as we shift our thing around, okay? So let me just kind of demonstrate. So what if instead of assuming an effect size of 0, we assumed that the effect size was 3, okay? So here, our pretend population, we're going to still use that, okay? And this is kind of the manual way. And here I'm going to just throw in this parameter value of 3 here. Okay? And you can look at the code, and it's pretty much exactly the same here, except here our difference is going to be the difference between these randomly sampled groups plus the parameter value here. Okay? So, I'm going to just repeat this 10,000 times, calculate, randomly sample with replacement from the vector of achievement levels, split those into group 1 and group 2, calculate the difference between those two group means, and then I'm just going to tack on a parameter here. So, I calculate this, and then over here, because I'm, here, let me just plot the density. Okay, so you can see it pretty much is the same thing, and now it's centered around 3, okay? And I'm going to ask, what's the, if we want to know what's the probability that it's at 5.9 or greater, okay? So we're going to draw basically a vertical bar at 5.9 and shift shade to the right. So in our case, we can see, how often did this happen? 1609 times. We can ask, what's the approximate p-value there? And now this has happened about 16% of the time, okay? And if we look at the mean and standard deviation, we see that the mean is around 3 and the standard deviation is around 2.95. Okay. I could do the same thing using the boot function in R. We'd create a function, data, indices, and here, in order to calculate the difference, it's just the mean. We've subsetted this, the first 34, the last 116, and tacked on 3, and we would get pretty much the same thing. Okay, this is just using the boot function. So it runs there, and here our approximate p-value according to the boot function is around just under 16%. Okay, so but right around 16%, as we might expect. Okay, so what I'm going to do is I'm going to repeat this process using a variety of kind of assumed effect sizes or assumed differences here. So I can start off by assuming, what would happen if we said the difference was 0 and we calculated that the p-value would actually be half of that, because it would only be so if this thing is centered at 0 and we go to 5.9, we can ask, what's the probability that we're at 5.9 or greater, okay? So rather than just repeating the same process over and over and just changing this manually from 3 to 4 or something, I can do this over and over again. So I'm going to create a results matrix, which is going to be, we're going to start at 0 and go through 12, so I'm going to have 13 rows and 3 columns. And I'm going to name my column names the p-value and the mean and the standard deviation. And I could use either my manual method or using R's bootstrap function. I'll show you guys doing it both ways. Okay? All right, and so basically on the inside, I'm going to have this inner loop, which basically just does exactly what I did before. We're going to take the random sample, randomly sample. This is what Bootstrap is. Okay, sample with replacement. Split them into 2 groups and tack on this parameter value. 0, 1, 2, 3, all the way up through 12, basically. Okay, but I'm going to repeat this 13 different times, each time using a different parameter value. So I'm doing j in 1 through 13, and so my parameter is going to go from 0 to 12. I'm going to go from run j minus 1, so it's going to run from 0 to 12. Each time I'm going to reset a difference vector, and then the results will be if the parameter is less than the observed difference. So if right now our observed difference is 5.9. So if my parameter is less than that, what we want is differences that are 5.9 or greater to get our p-value. Okay, but as we shift the distribution along the axis, so it's centered from 0 to centered to 5 to centered to 7 or whatever, as we shift it in that direction, the idea of getting our data or something more extreme is going to shift from looking to the right to looking to the left. So when a parameter becomes greater than our observed difference, now we're going to be looking to the left. And so that shifts it right here. Okay? The mean and the standard deviation, this will still just remain the same. So this is my great outer loop. And it just runs, doing 13 cycles of 10,000 each. Runs it pretty quick. And this is what we get. Okay? So when our assumed difference is 0, we're getting a p-value of around 2%. Okay? So we have strong evidence, or you know, a decent amount of evidence to support the alternative hypothesis, okay, in this case that there is a difference between the educational achievement of immigrants coming from Mexico versus other Latin American countries. If the alternative is that the difference is that those coming from not from Mexico end up getting higher achievement levels on average. Okay, and then, but if we're assuming that the effect size is, you know, something around 3 or 4, you know, now we have a lot less, or almost, you know, no evidence supporting this. Okay, or marginal amount of evidence, or negligible amounts of evidence supporting the alternative. Okay, this shows that it is quite possible, if the true effect size between groups is 4, then this means that it is quite probable to get an observed difference of 5.9. Okay, if the true effect size is 4. And likewise, if the true effect size is 8 or 7 or something like that, you know, what's the probability of getting an observed difference of 5.9 or something less? If the true difference is 8, then that's still quite high, okay, from random chance alone. Or not, well, if the null hypothesis were true. But as that effect size gets larger and larger and larger, then it becomes less likely for us to observe this data while the null hypothesis is true. Okay, and so this can also give us a bit of an idea of, you know, kind of almost like a confidence interval for the for what we might call plausible effect sizes, right? And here I just checked out integer values from 0 to 12, but we can say that, you know, if we're going to go from around 5%, something around there, we can say differences between 1 and 11 are plausible effect sizes for what we might for the mean difference in the population between immigrants coming from Mexico versus other countries from Latin America. Okay, so this would, you know, because if you wanted a 95% confidence interval, your cutoff points would be what, 2.5% and 2.5% on the lower bound and 2.5% on the upper bound, right? So if we want a 95% confidence interval, you know, we would roughly go from around 1 to 11, okay? And if we want to be more precise, we could further investigate more differences there, okay? And so this is under the assumption that that we have some stated effect size, and we can kind of just see, you know, what is the probability of getting our data if we assume that there was a specified effect size, and this gives us kind of a range of plausible effect sizes, effectively 1 through 11 in this case. All right. Are there any? Does this make sense? This process here? No. All right. The okay. And this is all covered in the textbook. So the textbook kind of walks you through this as well. I can just show you what this would look like if I used the boot package. Here, let me okay, multiple effect sizes with boot package. Okay, and so I would do, let's create our results matrix again. Okay, and so within each iteration, we're going to run this 13 times. I'm going to create a function called PV, and PV will be, instead of adding 3, I'm going to take the parameter value, which starts at j-1 and runs through 13. We're going to get our bootstrap model and our results. In results, basically we just want results j1, and we're going to do mean of model.boot $t. Greater than or equal to observed difference. I'll run this here. Okay, I think that'll do it. Did I? Oh, I have it spelled wrong. That will not do it. Okay. Modal. I don't know what this would be. Model. Model. Modal. Yodel. Okay. We'll try this. I hope it works. It's running. We'll see if our results. Ah, shoot. I called it PV here, but I have to replace it right there. Okay, now it'll work. So I think when I do it the manual way, because it's only keeping track of the difference, it actually runs a tiny bit faster than the boot function. But the boot function stores a little bit more. So, but anyway, let's take a look at results. And I think the results that we see here, I should not have deleted all of the other ones. I think they're quite similar. Let's see. 0225, 0499, 0395, 0213. Let's see. Similar. It's a little bit different, but yeah, well, 0.378, 0.487, 0.354. They're all within reasonable tolerances of each other. So yeah, seems reasonable to me. Okay. Okay, so that's using the boot package. I'll post the updated version of this file on CCLE as well, so you guys can take a look. Okay, we have an alternative model as well. Okay, and the alternative model doesn't mess around with a hypothesized effect difference. Okay, so let me just. So in all of these cases, we've been kind of testing, our null hypothesis would be something like mu1 minus mu2 is equal to 3 or equal to 4 or something like that. We're saying that this is the effect size that we're dealing with. Okay, over here we're not gonna be dealing with that. We're going to kind of just see all kinds of differences that we might observe. Okay, so here we're going to treat these as two separate populations, okay? So the alternative bootstrap model is that over here we've got population 1 has mu1, population 2 has mu2, okay? And we're basically want to create, make a confidence interval for mu1 minus mu2, okay? Which is what we're going to be dealing with here, okay? So here, what I'm going to do is I'm going to create two populations, okay? So I'm going to subset the achievement vector or achievement our data, okay? This is the vector of achievement levels, and subset those who came from Mexico and those who did not come from Mexico. Okay, so we have Mexican and non-Mexican right here, and now I'm going to create. What happened? Okay, so I have Mexican and non-Mexican, and here we're going to create random samples, sampling with replacement from the vector of achievement levels of those who came from Mexico, and sampling with replacement those who did not come from Mexico. Okay, so effectively I now have created two separate populations by sampling with replacement from these things separately. Okay, and then I'm going to calculate the mean from our first random sample and the mean from our second random sample, and we're going to calculate the difference between these two means. Okay, so this is different, right? So when we had the other one, we had the assumption that the two means were coming from the same population, and that's why we shuffled them all up, or we sampled all from the same population, and then we split them into two groups. Now we are saying they are two separate groups, and we're going to sample from the separate groups separately, and we're going to take a look at this difference. So here's just one example where I took one sample and we calculated this difference, and over here, that's interesting, I happen to get a difference of 5.96, which is quite similar to our another one. But if I randomly sampled these again, I could get quite a different result. Okay, so here I'm getting different results every time I take random samples with replacement from each of these things and calculate the mean difference there. Okay, so this is another way to look at it, and this effectively, we can create a confidence interval by doing this 10,000 times and then seeing the range of all of the different values that we see. Okay, so over here I'm going to create a new vector of differences. Maybe I'll call this differences. Okay, and each time I'm going to take a random sample, one for the people not from Mexico and one for the people from Mexico. Okay, each time, so we're treating these as two separate populations, and we're going to just randomly sample from these. Okay, so in effect we are turning our sample into a population by replacing by doing sampling with replacement. Okay, and then each time we take new random samples, we will calculate the mean between these two random samples. So I repeat this 10,000 times. Okay, and all of these things, the densities all end up looking quite similar. Something happened here. That was not quite right. Did I do something wrong? Oh, I still stuck with difference, not differences. Okay. Okay, and I mean it looks the same as before, but the underlying kind of the system that set this up is very different. Okay, and they all end up looking the same, and that's because of the central limit theorem, which applies whenever you take the mean. But so this happens, okay, and we can see kind of the mean difference, which makes sense, which is right around our observed difference, and the standard deviation, all of these things, is a little bit smaller, okay? And if we think about that, it should make sense a little bit, because here now I'm separating two two separate populations, so that's going to kind of reduce the amount of variance that we observe because we're kind of restricting ourselves when we do sampling to one group and sampling to a different group rather than throwing them all together. Okay, and in effect, there's a lot of discussion on how to create confidence intervals this way. One way is we can take a look at, here I did 10,000, so we can kind of sort these from, 1 through 10,000 in terms of the size of the difference, and I can basically find the middle 95%, so the middle 9,500. So effectively, I can find the observation, the 250th smallest observation and the 250th largest observation. Okay. The quickest way to do that is using quantile. Okay. So we would do quantile of all the differences we observed, and I'd say I'm interested in the 2.5th percentile and the 97.5th percentile, and this would kind of give me the differences for those two values. So we're getting a difference of around 0.7 to 11, basically. Okay, and so this is kind of a like a 95% confidence interval-ish type thing based on the 10,000 replications that I did. Okay, I did 10,000 this thing 10,000 times, and this is the one that happened at this is the 2.5th percentile, and this is the 97.5th percentile. Okay. Another way to do this is using the boot package, and the boot. If you use one advantage of using the boot package is there's a function called boot.ci, and this covers a bunch of different confidence intervals types based on Bootstrap, and I don't know, there's all sorts of maybe a few theoretical considerations that might go into this. Okay, a lot of times with Bootstrap you're not looking for an exact answer. Okay, so even though it says 0.6953499, you probably would not report this as as like the truth here. You would just say, well, because you're relying on your computer's random process. So if somebody else who does 10,000 replications is going to get something different. So when you're doing Bootstrap, you're not looking for exact answers. You're kind of looking for this ballparkish thing. Okay? So anyway, people talk about Bootstrap confidence intervals and the nuances behind the differences in each of these things. My opinion is they're all going to get you in the same ballpark, maybe. I don't know. Okay. So anyway, here we're creating a way to calculate the difference between the two things. Okay, and so again, here we are subsetting our data based on the indices, which is required whenever we do use the boot package. And this time, the way we're going to calculate this is we're subsetting based on the index, or on the column of whether they are from Mexico or not. We're going to say Mexico is equal to 0 versus Mexico equal to 1. Before, we just kind of said the first 34, the first 116 are in group 1, and then the remaining are in group 2. Here we are subsetting based on this property of whether they are from Mexico or not. Okay, and because it's looking at the original data set, this is going to work here. All right, and so we run this, and we give it this thing called strata in the boot function. Okay, and because we are effectively stratifying our samples based on whether they are from Mexico or not, so that's going to create kind of our indices separately here. And so we do that. We plot this density thing. It looks very similar to everything else we've done. Here, the mean here is 0.59, and our standard deviation is 2.64. So this is all very similar, okay? And we can create a Bootstrap confidence interval using some of the built-in functions. The results here will be a little bit different, again, because of some of these argued nuanced differences between different types of confidence intervals. But similar ballpark here. Okay, so here our bootstrap confidence interval is goes from 0.68 to 11.162, which is just ever so slightly wider than the one we have. You can look up the function boot.ci, and I think it discusses some of the different type of confidence intervals that you can create: norm, basic, student, percent, and BCA. Okay, I'll just do all, and I'll show you kind of. Oh, you need the variances for the studentized ones. Okay, and so you get slightly, slight variations on your confidence intervals, but they're all going to be quite similar to each other. Okay, and so this is a way to get an idea confidence intervals for these differences between groups from a computational perspective and a non-analytic one. Okay. All right, so we'll see you guys on Wednesday. I'll try to finish writing up homework 6 for you guys to look at and study from. So we'll see you there.